Hello everyone, I'm Sandor Bergi from the University of Bristol and I'm going to talk about my research on using scientific machine learning to augment physics-based models of nonlinear dynamical systems. So in this study, we aim to find data-driven models for nonlinear dynamical systems. This concept is linked to digital twins, which are essentially data-driven, adaptable, highly accurate virtual counterparts of physical structures that gained some significant interest in the previous years. Our approach to provide such models is to augment physics-based models of experimental systems with machine-learnable structures, thus creating universal differential equation models which we would like to train using measurement data taken from these experiments. The application I'm going to introduce in my talk will be Aeroelastic flutter, for which we both carried out numerical simulations, and we're also going to use some measurement data from an actual physical experiment. Most of the similar studies on dynamical systems try to identify a well-fitting model for a constant set of parameters, whereas our research, focusing on nonlinear dynamical systems which are frequently characterized by bifurcation diagrams, are inherently varying parameter problems, which means that these are more complicated from the point of view of the training procedure. Now, to put this into context, I first would like to talk a little bit about nonlinear dynamical systems in general. So these dynamical systems are described by nonlinear differential equations, where this function f in the right-hand side is a nonlinear function of the state variables x. Another important feature of this function is that it's also dependent on this parameter lambda, which will be referred to as a bifurcation parameter. Otherwise, these systems can be either autonomous or non-autonomous, and although for the sake of simplicity I'm using ordinary differential equations here, they can actually be differential equations of a more exotic type, like a delay differential equation, or one can also consider a nonlinear system described by a stochastic differential equation. In our study, we are specifically interested in systems with periodic solutions, an example of which is Hopf bifurcations, which is a feature in autonomous nonlinear dynamical systems. What happens in the supercritical case that initially we have a stable equilibrium, which as we start to increase lambda, reaching a critical point is going to lose its stability. However, from the stability boundary, we see another branch corresponding to stable periodic solutions emerging, indicating that in these parameter boundaries where we have an unstable equilibrium, the solutions we are going to convert to a large amplitude periodic solution. What is different in the subcritical case that here the emerging branch of periodic solutions is unstable. However, right, this is not true in general. It's relatively common that this branch later on undergoes a saddle node or fold bifurcation, and then the unstable branch becomes stable, and then the large amplitude limit cycles create a similar structure for higher values as lambda, as one can see for the supercritical case. Of course, identifying unstable solutions in experimental systems is not that trivial, because basically one can only gain direct information of them with using some sort of control. Therefore, it's reasonable to ask the question whether it actually makes sense to calculate and capture them. However, if we consider what these diagrams really indicate, it becomes obvious that they have an important role, namely that the unstable periodic solution gives us an indication about the boundaries between the domains of attraction of the two stable steady-state solutions in those so-called bistable parameter domains, where we have two coexisting stable solutions. This behavior, by the way, is usually seen as undesirable in engineering systems because this means a sort of unpredictability and the dependence to the initial conditions. The reason I mentioned engineering systems is basically because these kind of structure with the Hopf bifurcation, either the supercritical or the subcritical one, can explain plenty of engineering vibrational phenomena. For example, to mention two examples from aerospace, both aeroelastic flutter, which is basically the self-excited vibration of aerofoils causing the oscillation of the wings of this aircraft, and also wheel shimmy leading to the vibration of the nose landing gear in the second video, can be explained by similar Hopf bifurcations. Right, so after this introduction, let's take a look at our modeling concept. We are basically assuming that we have an experiment with an underlying nonlinear dynamical system, and we also assume that we are capable to measure the bifurcation diagrams indicating the periodic solutions in the system. Now, usually the case with real experiments is that one often has some kind of knowledge and insight into how the system actually works. Therefore, in most cases, it's possible to come up with a physics-based model, which is not necessarily 100% accurate, but at least it's capable to describe how the system behaves in a qualitative sense. Then what we would like to do is basically to add the universal approximator, either a neural network or a Gaussian process, to make a universal differential equation model, which we would like to train such that it's not just qualitatively but also quantitatively accurate. So the intended effect can be seen in the right hand side when we have an observed periodic orbit indicated by the black curve. Then we have a prediction from the simpler physics-based model indicated by the green curve, and then we would like to add the universal approximator to get the red curve, which, as you can see, fits relatively well to the observed behavior. If we would like to express our concept in terms of equations, then we consider the differential equation of the dynamical system in a stochastic form to allow for process noise in the system. Now, usually the problem with experiments is that one can only use a finite number of sensors, therefore we can't get information from all the dynamical phenomena going on in the experiments. In most of the cases, we only measure the most important ones. Therefore, it's reasonable to distinguish between an accessible and a hidden part of the system, and then what we can essentially do is that we make a physics-based model using all the accessible state variables, and then we would add the universal approximator to compensate the error caused by the neglection of the hidden dynamics. As I mentioned before, we are considering two types of universal approximators, neural networks and Gaussian processes. In the following slides, I would like to highlight the differences these two types of universal approximators are considered in these models. For example, neural networks are used with the DFQ flux package in Julia, which basically makes predictions for the trajectories of the universal differential equation. Then, based on these trajectories, we can calculate the error between the prediction and the measured trajectories, coming up with an overall error measure, which will serve as the objective function of our optimization. This is a little bit different with Gaussian processes. One of the main differences is that Gaussian processes are capable to consider noise in the system, which makes them useful for cases when we have a considerable random excitation. But the other difference is that in this case we fit directly to the right-hand side of the differential equation instead of the trajectories. Another difference is in the number of parameters needed to be optimized, since the Gaussian processes use significantly less parameters than the neural networks. This basically means that in different cases one may find Gaussian processes or neural networks more useful than the other. Right, so let's take a look at a practical example, Aeroelastic flutter. As I mentioned in the beginning, for this example we are using both simulational and experimental data. For the numerical simulations, we are considering a 2+1 degrees of freedom model of an aerofoil in an airstream as an underlying model of an experiment. This model has two physical degrees of freedom, the heave and the pitch motion of the aerofoil, which we consider as the accessible state variables of the system, whereas there is a third hidden degree of freedom in the system related to the aerodynamic effects. Therefore, the universal differential equation model of this system consists of a simpler physics-based model of the aerofoil using just the heave and the pitch degrees of freedom, and then we would add a machine learnable structure to consider the aerodynamic effects in the system. Now, if we did the training of the universal differential equation model using deterministic simulational data, using neural networks as a universal approximator, then this approach basically provided us perfect results. So in these bifurcation diagrams here, the thin curve indicates the periodic solutions in the pure physics-based model, whereas, as you can see, the universal differential equation model could be fitted to the measurement data indicated by these orange crosses with almost perfect accuracy or very good accuracy. Of course, the previous case wasn't very realistic, so then we start to pollute the system with a little bit of noise where we could utilize the Gaussian processes. And as you can see, if there was only a moderate amount of noise in the system, then even though the fit is not 100% perfect, we still get a really good fit to the measured trajectories. However, we also found that actually there is a limit until one can go with the Gaussian processes. First of all, because the signal-to-noise ratio was important in these cases, and unfortunately, since we are using acceleration data here, this was very sensitive to the amount of noise added to the system. But we had another bottleneck as well, namely that the Gaussian processes don't scale really well if larger amounts of measurement data is used. Therefore, they were not very suitable for more complex problems. Basically, this is the reason why we eventually choose to use a neural network for the experiment done in a wind tunnel with an actual wind profile, even though this required a bit of preconditioning of the measurement data to make it quasi-deterministic. Well, as you can see, with this type of universal differential equation model, we were able to identify a relatively well-fitting system that's capable to replicate the measured bifurcation diagrams. However, unfortunately, what we found that the previous model in this diagram was not very robust, and actually it was very sensitive to the initial guess and also to the parameters of the optimization algorithm, which was very prone to converging and finding local minima instead of the global minimum of the objective function. Therefore, one of the main conclusions of these analyses is that although this approach has really great potential in finding nice models, nicely fitting models for nonlinear dynamical systems, one certainly has to address the issue of robustness. Therefore, the next steps we are considering for this analysis is basically changing the current initial value problem-based training for neural networks to a boundary value problem solver. Because basically currently within the DiffyQ Flex package, we do not directly use the information that we are actually looking for periodic solutions, and actually making simulations forward in time is not the most optimal way of finding periodic solutions. For example, in most of the numerical bifurcation analysis software, they tend to use the technique of numerical collocation. Therefore, in the future, we would like to make the training procedure to work with a boundary problem solver, and we expect this to be improve the robustness of the training procedure. So to summarize my talk, as you could see, both neural networks and Gaussian processes were used as universal approximators for the database augmentation for physics-based models of Aeroelastic flutter. As the examples indicate, this could be done with varying success. Some of the examples, mostly the simpler ones, were nicer, some of them were not so nice, which basically indicates that your mileage may vary within the current training framework. Therefore, there will be always a little question about how much credit we can actually give to these identified models, which highlights the importance of the robustness of the training procedure, which unquestionably needs to be improved a little bit. And as I mentioned, we have some plans to changing the solution to a boundary value problem solver, which we hope would make the training procedure more robust. With that, I would say thank you very much for your attention, and I would like to acknowledge the support of EPSRC for our research.